Cluster sampling. This is the introduction. Cluster sampling is a technique used where the total population of a place that you're trying to estimate values of is divided into different groups which share common characteristics, and these groups are called the clusters. An example of cluster sampling is having classes in a school as the clusters, where the elements come from the individual students, such as their grades, if you're measuring the performance of the school. The required data is then gathered by taking a simple random sample of the elements in each group. Cluster sampling can be one stage, which is where all the elements from the selected clusters are used in the sample, or it can be two stages or more, multi-stage, where only a certain number of elements from each selected cluster is used in the sample. Multi-stage is used when the clusters are large or particularly homogeneous. Cluster sampling is used to group homogeneous elements in one cluster to reduce the total variation in the population, so grouping by age or class subjects. You can also use cluster sampling on smaller populations to get a better estimate of the overall population if you can't take a sample from that, such as if it costs too much money to do. Here's an example of cluster sampling. Here we have 3 different clusters. Only 2 of them have been picked to be used in the sample, and in the sample 3 elements from the first cluster are used and 2 elements from the third cluster are used. So there are advantages and disadvantages of cluster sampling. Cluster sampling is an easy method to use when trying to estimate values for a large population, because you can simply split a smaller population into the relevant clusters and then use that data to estimate your overall population values. However, this results in less accurate results than most other methods because it's largely dependent upon the clusters, and the surveyor may over or underweight one particular cluster, which would lead to skewed results. Clusters can be limited by their features, meaning that certain parts of the population can't be included in the survey because they don't fit a cluster, which means that the estimate of the total population does not take into account all of the elements of the population. The population will be divided into n separate groups, which are the clusters. These clusters can also be referred to as primary sampling units, or PSUs, where the elements in these clusters are the secondary sampling units, or SSUs. Yij is used to denote the jth value for the ith cluster. So, say a student's grade, the jth student's grade in the ith cluster. N clusters are then selected to be included in the sample. So capital N is used to show the total number of clusters used, and little n is the number of clusters picked for the sample. The number of elements in cluster I is defined as Mi, and the number of elements in cluster I for the sample is lowercase mi. So for one-stage sampling, since all elements in each cluster are used, lowercase mi is equal to uppercase mi. T is the population total, where lowercase t dot is the estimated population total. Ti is the population total for cluster I, and Ti bar is the estimated population total of cluster I. I bar is the mean over all clusters, whereas lowercase y bar I is the sample mean for cluster I. S squared is the total population variance, and the ICC is the intra-class coefficient. So, this is how you estimate the population total and the population mean for one-stage cluster sampling. We know first off that M is equal to Mi for all I because the clusters are equal size. The unbiased estimation of the population total T dot is calculated as n over n times the sum of Ti over all i's. As an example, say we're trying to measure the performance of students in a class by checking their grades. The population of the class is our total population. This is T. It's divided into 3 ages in this case, which act as our clusters, which means that capital N equals 3. Each age group has 3 students in it, which means that capital M is equal to 3. The students' grades for the first class, N1, are given as 80, 75, and 80. For the second one, they're given as 70, 60, and 64. The third age group, N3, has grades of 75, 78, and 68. In this example, let's say that we use 2 clusters, which means that N1 is not in the sample. So the sum of the TI over all i's used in this sample would be the sum of the elements from clusters 2 and clusters 3, which is 70 plus 60 plus 74, plus 75 plus 78 plus 68, which comes to a total of 415. T dot is then equal to n over n, which is 3 over 2 times 415, which is the sum of the TI's, and that comes out to be 622.5 as our estimate for T dot. The estimate of the population mean is then given as T dot divided by the population total, which is n times m, which in this case is 3 times 3, so you divide 622.5 by 9, and you have 69.17 as our estimate of the population mean, and 622.5 as our estimate of the population total. For multi-stage clustering, you're going to need to estimate the TI's before you can work out T dot, because you don't know which elements are going to be used in the cluster for the sample. So Ti is equal to mi times 1 over lowercase mi times the sum of the clusters used in the sample with their elements that are used from the cluster I. So say you take the first and the third element from the first cluster and the second and the fourth element from the second cluster. And this comes out to be equal to the capital Mi times y bar I, because y bar I is the sample mean for cluster I, and that's what we are calculating here in the sum. The population total is then worked out in the same way, except you use Ti bar rather than Ti, and you come back here. That line would just be worked out in a different way, and then this one and this one would be done the same. Okay, so the next thing to do is the sampling variance. So the sampling variance of the population total is 1 over capital N squared times m squared times the variance of T dot. As we know that T dot is equal to n over n times the sum of the TI's over all i's, we know that T dot is equal to n times y bar, which is the overall population mean. So the variance of T dot is equal to n squared times the variance of y bar. And we know from theorem 5.2 that this comes out to be n squared over n times the standard deviation of t squared times 1 minus n over n. So the sampling variance for the mean is going to be the same as this, except you replace T dot with T dot over the population total, which gives a sampling variance of 1 over n times m squared times the standard deviation t squared times 1 minus n over n. So for multi-stage, the sampling variance in multi-stage sampling, you will need to estimate the between cluster variance and the within cluster variance. So the between cluster variance, lower s t squared, is estimated as the sum of all clusters included in I of Ti bar minus T dot on n, all squared, and then this is divided by n minus 1. This is also an estimate of the true variance of Ti. So the within cluster variance is lowercase si squared, and it's equal to 1 over mi minus 1. And then all of that is multiplied by the sum of yij minus the sample mean of cluster I squared. We also calculate the finite population correction for each cluster, which means that FPCI equals 1 minus mi on mi. So the finite population correction is simply 1 minus f. So now we have that the sampling variance is a combination of the two earlier terms, which we have is n squared times FPC on n times st squared plus n over n times the sum of all clusters included in I of FPCI times mi squared times the standard deviation of I squared on mi. Obviously this is much more complicated than the single stage one because you have to estimate, you have to find your lower m's. The sampling variance for the population mean is calculated in the same way, except you replace t bar with t bar on the population total, which is n times m. So here's an example of how to calculate sampling variance. Say that m1 equals m2 equals m3 in this case, which means that they're all equal to 500. y1 bar, which is the population mean for the cluster 1, is 1000. y2 bar is 1250 and y3 bar is 1300. So we have S1 equals 2200, S2 equals 3200, and S3 equals 4000. The sampling variance for the single stage is then 1 over n times m squared times st squared times 1 minus n over n. So let's just assume that lowercase n equals 2, so we're using 2 clusters, that capital M equals 500, and that st squared, actually, those 500 should be 50s, slight error. So st squared equals 9400. And then the sampling variance is 1 over 5000 times 9400, which is st squared, which is the sum of the other s's. And then you times it by 1/3, which is 1 minus n over n, which is 1 minus 2/3, which is 1/3. And this comes out to be 0.627, rounded to 3 decimal places. The next thing to look at is the intracluster correlation coefficient. This is the common correlation in pairs of observations from a cluster. So to do this, we have to split the variance into the between cluster variance and the within cluster variance. So the total variance here is equal to the within cluster variance plus the between cluster variance. So we know that ICC is equal to 1 minus the within cluster variance over the total variance. And this is also equal to the between cluster variance over the between cluster variance plus the within cluster variance. So ICC can also be estimated as 1 minus n over n minus 1, and that all times the within cluster variance over the total variance. This is because n over n minus 1 is just equal to 1 for sufficiently large n. So from this formula, you can see that ICC is equal to 1 when the within cluster variance is equal to 0, because that term would just go away. And we know that ICC is equal to -1 on n minus 1, which is at its minimum when the between cluster variance is equal to 0, because this figure here is equal to the standard deviation minus b. So we have standard deviation over standard deviation, which is 1, and then standard deviation of b on standard deviation, which is 0. So this thing just becomes 1. We have 1 minus n over n minus 1, and that comes out to be -1 on n minus 1. Okay, the design effect. The design effect is the ratio of the variances for 2 different designs, with the same number of sampled elements used in them. Usually the denominator here is the variance that you get from using simple random sampling, because this is the base comparison method. In this case, the design effect is equal to 1 plus m minus 1 times the interclass correlation coefficient. This means that the design effect is equal to 1 when the ICC is equal to 0. You can also see that a larger cluster size will clearly increase the design effect, because unless ICC is less than 1, because it will just cause this figure here to get larger, which will cause the design effect itself to get larger. So an ICC of less than 0 is going to lower the design effect, because you'll take away a ratio of this from 1, and if it's greater than 0, it's going to cause the design effect to be large, because you'll have 1 plus some ratio of this. So, to calculate an effective sample size, once again assuming that the clusters are of equal size, all you have to do is find an n that you want to use from the start, and then you divide it by the design effect. So the effective sample size is equal to the first sample size divided by the design effect, which is 1 plus n minus 1 times the intraclass correlation coefficient. So here's an example of how to calculate these. To calculate the ICC, we need to know two of the standard deviation, the standard deviation within clusters and the standard deviation between clusters. And sorry, that's all variance, not standard deviation. And all of this can be calculated using SAS. So let's say that we have a standard deviation of 2.4 and a within cluster standard deviation variance of 1. We can figure out from this, since standard deviation equals standard deviation W squared plus standard deviation B squared, that the within the between cluster variance is equal to 1.4. Let's assume that lowercase n is 150 for our first go, and that the number of elements in each cluster is 50. So we have an ICC equals 1 minus n over n minus 1 times the within cluster variance over the total variance, and this is equal to 1 minus 150 and 149 times by 1 divided by 2.4, and this comes out to be 0.58, rounded to 2 decimal places. And since this is greater than 0, we can tell that the ICC is going to cause the design effect to be higher. So yes, the design effect here is equal to 1 plus n minus 1 times ICC, which is 1 plus 49 times 0.58, and that comes out to be 29.42. So we can now calculate the effective sample size, which is just 150 divided by 29.42, which comes out to be 5.099, rounded to 3 decimal places, and this is rounded up to 6 to ensure that we have everything in our sample size. So cluster sampling can also be seen as an extension of systematic sampling, or systematic sampling itself can be extended and it fits a one-stage cluster sample, which means that all m's are equal. So for an example, say that we have a population that has 50 elements, and we want to take every 10th element to make up clusters. So our clusters are 1, 11, 21, 31, 41, and then that's our first cluster, our second cluster is 2, 12, etc., and our last cluster is 10, 20, 30, 40, 50. Here we're clearly using systematic sampling to pick the elements for each cluster, so we're using systematic sampling to create our clusters. The variance of this is calculated as the total variance divided by m times the design effect. So if ICC is equal to 0, then this variance is the same as it is for simple random sampling, because you just have the standard deviation total divided by m, because that becomes 0 and it's just that times 1. Last of all, if the ICC is less than 0, then the variance will become smaller, meaning that this method is more effective to use than simple random sampling. If the ICC is greater than 0, then the variance will be higher, and this method is clearly less effective than simple random sampling. And these are used. Thank you.